demonstrating you the fifth experiment. Op-amp has an adder, differentiator and integrator. So the aim of this experiment is to design an adder, differentiator and integrator circuit using op-amp. So first let us see the design of an adder circuit. So here is the circuit diagram of adder circuit. So we need to use op-amp, that is MU-A741 IC. Okay. Here pin number 2 and 3 are the input terminals of the op-amp. 7 represents plus VCC and pin number 4 represents minus VCC and 6 is the output pin. So here we are providing two input signals. Okay, so both the input signals are shorted and given to the pin number 2. Here pin number 2 is called the inverting input terminal. Pin number 2 is inverting input terminal of the op-amp. And also a feedback resistor RF is connected between the inverting terminal and the output terminal. So this resistance, it acts as a feedback. And pin number 3 is directly grounded here. We are providing plus 12 volts VCC to pin number 7 and minus 12 volts minus VCC to pin number 4. And we are measuring the output at pin number 6. Here we are providing two input signal. One is the AC input signal of amplitude 2 volt peak to peak and frequency 1 kilohertz. This signal is provided from the signal generator, and one more input signal is provided from the power supply. This is a DC signal of amplitude 1 volt. So both the input signals are provided through resistors of range 10 kilo ohm. Okay, so this is the circuit diagram of the adder circuit. Now let us see the design. How to design, how to get the values of the resistances here. So the output equation of the adder circuit is V0 equals minus RF by RI into VI plus V reference. Here VI is the AC input signal and V reference is the DC input signal. So this adder circuit, it performs the addition of both the inputs. So, you can observe here both the inputs are applied to the inverting terminal. So the output is inverted here. So we are getting the minus sign here. Okay. So V0 is equal to minus of RF by RI. RF is the feedback resistance and RI is the input resistance. If we assume unity gain is nothing but V0 by VI, input, output by input voltage. So if output by input is equal to 1, then RF becomes equal to RI. So let us choose RF equals RI, that is equal to 10 kilo ohm. So we got RF and RI values as 10 kilo ohm. So this completes the design of the adder circuit. Now let us see the input and output waveforms. So VI is the AC input signal. So we are providing a sine wave as input here of amplitude 2 volts peak to peak. Can observe here it is of amplitude 2 volt peak to peak. And one more input signal is the DC signal of amplitude 1 volt. So DC signal, it's a constant signal. So a constant of 1 volt signal is provided. So when both the signal gets added, here is the output waveform. So the output waveform will be like this. See, this is the input signal. So for this input signal, when a DC signal gets added, the output in the output this signal gets shifted. Okay, so when it gets shifted, it will be like this. But since the op-amp is connected in the inverting configuration here, this is an inverting summer circuit or inverting adder circuit. So this signal gets inverted. Okay, so you can observe here the signal is inverted here, and this is 0, this is the reference axis, and we can get this origin at minus 1 volt. Okay, so the output gets inverted here. The addition of the two inputs gets inverted at the output. So this is the adder circuit. Next is the differentiator circuit. So this is the circuit diagram of the differentiator. So which consists of op-amp MUA741. Here input is provided to the inverting terminal of the op-amp, that is to the pin number 2. Here input is given through capacitance, okay, and feedback component is the resistor here. So resistance is used as the feedback component. So the output signal frequency, it depends upon RF feedback resistance and the capacitance. Okay, so what is a differentiator circuit? Actually the differentiator circuit, it produces the differentiation of the input signal. So mathematically the output equation is V naught of t is equal to minus RC. Here RF indicates the feedback resistor. So RC into dV in by dt. So we can observe here the output is directly proportional to the differentiation of the input signal. Okay. So this is the output signal. So the output frequency, the output signal frequency is given by F equals 1 divided by 2 pi RFC. Here choose F as 1 kilohertz, then C as 0.01 microfarad. Then substitute these two values in this formula, F as 1 kilohertz and C as 0.01 microfarad. After simplifying, we get the value of RF as 15 kilo ohm. Then choose C equals CF, that is equal to 0.01 microfarad. So initially we assumed C as 0.01 microfarad, that is this capacitance value. Let us choose CF equal to C, that is 0.01 microfarad. See, practically we used to connect now one more feedback component, that is capacitor, in parallel with the RF. So what is why we need to connect this is in this feedback capacitance, it provides the stability and reduces the noise in the output. Okay, that is the function of this capacitance. In order to provide the stability and to reduce the noise, we are going to connect the capacitance in parallel with the RF. So this is the differentiator circuit. Now let us see the input and the output waveforms. So here input is provided with a square wave of 2 volt peak to peak. Okay, so when input is square wave, the differentiation of the square, we get a spike signal. You can observe here we are getting a spike signal here. Here also you can observe for a rising pulse, for a rising edge, you are getting inverted. Okay, whereas for falling edge, you are getting the rising pulse. So the signal is inverted since the input is given to the inverting terminal of the op-amp. Okay. Similarly, if we provide sine wave as the input, then the differentiation of sine wave is cosine. So for sine wave, we will get a cosine wave. Here only you can observe. Now what is cos? This is cos of this 0 is 1. So you are getting the waveform starts at 1. Okay, that is minus 1. It is inverted, so it is starting at minus 1. So like this is the differentiator circuit. One more circuit we have, that is the integrator circuit. So for integrator, just we need to interchange the components of R and C. So here you connect C of value 0.01 microfarad, and here we need to connect R to the input. So R is of same value 15 kilo ohm, and here the feedback component now is the capacitance of value 0.01 microfarad. The design is same, but here we need to connect the resistance. Okay, so let us call this as RF. The value of this resistance is 10 times the R. So here we have the value of R as 15 kilo ohm. So 15 kilo ohm into 10, we get 150 kilo ohm. Okay, so this is the value of RF. So in this way, the design for RF, R and C is same. The design is same. To get the value of this RF is equal to 10 times R. So R value we got 15 kilo ohm. 15 into 10 we will get 150 kilo ohm. So this is the design of the integrator circuit. Now if we provide square wave as input to the integrator circuit, okay, so for integrator we get the inverted triangular wave. Okay, for if we integrate the square wave, we get the inverted triangular wave. Similarly, for sine wave, we get the cosine wave, but the cosine will be like this. Okay, so integration of the sine is cosine. Here the output equation for the integrator is minus 1 over RC integration of input, okay, into dt. It ranges from 0 to t. Here RC minus 1 by RC is the time constant. Output is integration of the input signal. So this completes the design of the adder, differentiator and integrator circuit. Now we shall see the demonstration of all the three experiments.